Okay, so in this video I'm going to be proving the SUVAT equations. So in the SUVAT equations, S represents distance, U is initial velocity, V is max velocity, A is acceleration, and T is time. Here they are. So we've got V equals U plus AT, S equals UT plus 1/2 AT squared, S equals VT minus 1/2 AT squared, S equals V plus U over 2 times T, and V squared equals U squared plus 2A times S. Okay, so we'll go from the top. So let's start with this one. So a rule is that if you have a velocity graph, an acceleration graph, the velocity graph is the integral of it. So we know that V equals the integral of our A. Okay, now in the SUVAT equations, they're dealing with times when acceleration is a constant. So like, for instance, when you drop something, the acceleration it has downward is a constant, which is 9.8 in that case. But yeah, so the graph for acceleration in this case will, if there's my axes, it'll just look like that. It's just a constant across. With that in mind, you would probably know that it's like a rectangle, right? So the area under it, the integral, is going to be its height, which is acceleration times time. So V equals AT. Now this is an integral with without a range on it. So we do plus C, but we don't know what that C is yet. But we can figure it out because when t equals 0, this equation has to equal the initial velocity. Obviously when t is 0, this cancels, so C must be the initial velocity. So V equals AT plus your initial velocity, U. Right, that's the first equation. So the second equation is this one. Basically what you're doing on this one is writing distance in terms of acceleration. So S is the double integral of acceleration, or the integral of velocity. Now we already have this equation, which is the first integral of acceleration. So we can swap the first integral and the acceleration for that. So we have S equals the integral of AT plus U. And now what we have to do is integrate this. So the AT, you raise the power by 1 and then divide by that power, so that's 1/2 AT squared, and then for the U, we just do UT. Assuming there's no initial distance, this plus C would go away, but if you had an initial distance, you could add that on there. Okay, so that's the second SUVAT equation. The third one, we're going to make a little formula and then substitute it into this one. What we're going to do is we're going to write UT in terms of VT. So to do that, we have this equation here, okay? So let's have a look at that. We have V equals AT plus U. Okay? I want to write UT in terms of VT. So let's multiply both sides by T. So we get, on this side we have VT equals AT squared plus UT, just like that. And then all we have to do is subtract AT squared from both sides. So we have UT equals VT minus AT squared. So now what we're going to do is we're going to take this formula here and we're going to plug this in, because obviously ut equals this, so if we swap it in, the formula will still be good. So let's go do that. So we have s equals 1/2 at squared, and then instead of our ut we're going to have plus vt minus at squared. And then you can see you have plus 1/2 at squared minus the whole at squared is just going to be s equals vt minus 1/2 at squared. Just like that. Okay, so that's our first three SUVAT equations.